Welcome to the next webinar in the Coffee Breaks with NenoVision series. My name is Veronika Hegrová and I'm the Application Specialist of NenoVision Company. This webinar is focused on measuring with LiteScope. Just to remind you that this streaming format is pre-recorded, so you can ask your questions using Q&A chat window. My colleague and I can answer your questions during the stream, and if there are any important questions, I will do my best to answer them loud by the end of the webinar section. Welcome to today's presentation, focused on measuring with LiteScope. LiteScope represents a unique atomic force microscope, which is designed to be easily integrated into a variety of scanning electron microscopes. AFM and SEM enables us to combine the benefits of each of the methods itself and to obtain as much information about the sample surface as possible. Before we start measuring, I would like to point out a few of the LiteScope features. LiteScope is operated in NanoView Software, which is quite intuitive and easy to learn. You can measure with different probes using diverse layouts, which are very similar. So if you learn one method, you can easily measure many of the AFM techniques, depending on the probe used. Also, the operation software of the LiteScope, NanoView, is web-based, so we can access with no installation from any computer connected to the internet or even via Wi-Fi from your phone. Here, I would like to quickly go through the measuring procedure, which we will later discuss in more detail. First, if we would like to measure in SEM, we place the LiteScope inside the SEM chamber. Otherwise, we can also measure just AFM techniques on the table, as today's measurement. Further, we start the NanoView software choosing the layout according to the selected probe and the technique. The software is very intuitive, so after finding the area of interest and adjusting a few parameters from the layout, we observe the sample surface and process the obtained data. The integration of the LiteScope into SEM is very fast and possible into several SEM brands. Now let's have a look how to do it. We are going to replace the SEM sample holder by LiteScope. First, we fix an adapter to the stage. The adapter differs according to the SEM brand used. We rotate the stage to the proper position, and then we fix the LiteScope with 3 screws to the adapter. Finally, we connect the LiteScope cables into the feed-throughs leading to NanoBox. We are going to start the NanoView software by which the LiteScope is operated. First of all, we log in and select the layout, and then I will introduce you a little bit of the NanoView interface. Via IP address, we log in to the NanoView software in a browser and lock the microscope. Now, no user but you can operate the LiteScope. We create a new project, or we can choose an existing one where we would like to save the data. We can double check that the folder was created in a browser. Then we select an appropriate layout according to the method and probe used. You can either choose one of the layouts or create one of your own. As you can see, there is many of them already created. Here we are going to measure AFM topography with Akiyama probe, so we use the layout Akiyama. I would like to introduce you the NanoView interface, that you know what you are looking at in the layout. On the upper left, we see the active project and the layout. All the options are in the right menu bar, which will open you a tab window, as you can see the scan and browser in the tab bar. In the left column, we control the measurement from choosing the scanning direction, setting the image parameters through feedback control, AFM tip movement by macromotors box, to the signal observation selection and saving the data. The right column shows us the scanner position and monitors the measurement. We can also add a node here, which will be saved within a file. The central column is reserved for observed data visualization, where we can choose which channels we would like to see. The operation in NanoView remains intuitive if different probes and so layouts are used. The arrows show the changed parameters for piezoresistive probes in contact and in tapping. Only feedback control, channels, and data monitoring changes. Like this, different techniques such as conductivity measurements, STM, etc. can be easily observed. Anyway, the layouts can be changed by each user, so you can transform the layout in your account as you wish. Let's get back to our measurement. As we have chosen Akiyama layout, we are going to load the commercial Akiyama probe and navigate it to the area of interest. We place the probe into a probe holder using tweezers. Flip it over. And load the probe into the holder in LiteScope. Let's find the area of interest on the sample surface and move the tip closer to this area. We are going to use the macromotors box. Here shown on the right, we set the step value and move the tip according to this step in all X, Y, Z directions. To move finer, we decrease the step value and continue moving the tip. The tip is pretty close to the surface, so now we need to sweep the probe to find its resonant frequency before approaching to the surface automatically. First, we go online to turn the preamplifier on and open Phase Locked Loop tab from the menu bar. We press Start to sweep the probe using default parameters from the layout. The tuning fork of each probe requires different compensation, which we need to adjust in the probe offset box. If we have a look at the amplitude values, it should be around 0.5. We need to increase the sine amplitude value in sweep settings. Also, the frequency range is too broad for exact resonant frequency determination. For that reason, we zoom in by dragging from the graph edges closer to the peak. The correct range width is approximately 100 Hz. We sweep for the last time and select the working frequency. Pressing Auto PLL enables phase and amplitude feedback and starts to vibrate with the tip using the selected excitation frequency. As we switch to the scan panel, we start approaching the tip. The tip is now approaching to the surface automatically. In the upper right corner, the moving red scale and the Z-axis graph below schematically show the piezo expansion and contraction. The piezo under the scanner is moving towards the tip as the probe does not detect the voltage of the set point. The piezo is contracted and the probe jumps 50 micrometers down by macromotors. The process is repeated till the tip is in contact with the sample surface. Because the piezo is expanded too much here, we use the withdraw button and get the tip closer to the surface by macromotors. When we enable the feedback, the piezo is expanded again, moving the tip to the contact. As we approach the tip to the surface, we are going to set and adjust the image parameters and measure the sample surface. On the left, we start the scan in the scan control box and correct the surface tilt visible as a slope of the graph by slope correction in the right column. Then, we improve the feedback by increasing the set point and lowering the parameters to slower the feedback loop. On the right side of the images, in the center column, there are several functions how to improve and so point out the surface features of the obtained image in the software, such as rose alignment, contrast adjustment, etc. Now we can change the scan direction from top down to left right, and we correct the slope of the scanning in the right angle. As the feedback is set, we adjust the image parameters. We increase the number of steps and leave the speed and overview scan range the same. We can change all of the parameters in the scan settings box when not measuring. We start measuring. I sped it up for now. In NanoView Software, you can measure along a line and see the dimensions in the graph, or you can change the toggle view to have diverse center column layouts depending on what you would like to see. Here we have only AFM signals because we are measuring on the table. We choose which one of them we would like to see. But the same way, we can choose appropriate signals in the channel select box if we are measuring in SEM. You can see that both SEM and AFM signals are now observed. When we return to our measurement, we can move the tip to the exact spot of the measured area thanks to the XY offset without retracting the tip. This way it is possible to measure, for instance, the force distance spectroscopy of the exact place. One of the other functions of NanoView is to choose the place in the obtained image. Like this, we can measure the selected detail either with or without changing the scan parameters. As you can see, we navigated the tip to the exact position of interest, and now we are obtaining the image. After observation of this detail, we are going to finish the measurement, so we don't forget to retract the tip. The last section is dedicated to post-processing of the obtained data. We can either download the file or whole folder of measured images. Before processing the data, we finish the work in NanoView Software by going to standby mode to turn off the voltage, unlock the user, and log out or shut down the software. The post-processing of the data takes place in Gwydion software. They are all signals saved together in one file and can be processed separately. As you can see in the right, there are also saved all measuring parameters from NanoView. Opening the topography in 3 dimensions enables us to see the true surface morphology. If we overlay the topography with other measured signals, and for example improve the light, we are able to obtain complex information about the sample surface. I would like to summarize what we discussed in this presentation. We went through a few measuring steps with LiteScope, including the fast integration to SEM. We have mainly focused on the NanoView software, which is intuitive and easy to use. I have shown you how to operate in NanoView on the topography measurement and sketch the use of other techniques and probes. I would like to thank you for your attention. Ladies and gentlemen, now we are starting the Q&A section. We have one question we'd like to clarify this way. The question is, can we check the quality of the probe if the resonant frequency is stable before measuring the detail? Yes, we can use the withdraw button in feedback box to contract the piezo. Then the tip is far enough so we can sweep the probe again, select new resonant frequency, and we can enable the feedback again, approach the tip to the surface, and continue measuring. If you have more questions, you can visit our webpage nenovision.com or contact us directly via email. If you have an interesting idea or application which you would like to hear from us, we are happy to discuss it with you or prepare a short entry specifically to this topic. Here, I'd like to invite you to watch our webinars on our webpage, where you can also follow the released news and upcoming events. With this, we are ending the series of coffee breaks with NenoVision. On behalf of the whole company, I would like to thank you for your attention.